All right, let's do a Newton's Law cooling problem. We did this problem today in class. So what happens is there's a 29-degree Fahrenheit cold storage room, and we find a body in there. So the ambient air temperature is 29 degrees Fahrenheit. We immediately record the body's temperature and note the time to be 4:42 a.m. Early in the morning. We call that time t equals 0. And the temperature at that time was 49 degrees. So here, this point right here on our graph, if we make a graph of this, this is temperature on the y-axis and time on the x-axis. And at time 0, the temperature is 49 degrees. We wait 1/2 hour later, so we wait 30 minutes, 0.5 of an hour, and we note that the temperature has dropped to 43 degrees. The normal body temperature is 98.6. Find the time of death, not how many hours, but the actual time of death, and the equation of exponential cooling for this problem. So we know it's going to be some problem like this. The equation is going to be something like temperature equals A times B to the x power plus K. And we know that K is the asymptote. In this case, because the ambient air temperature is 29 degrees, the asymptote is going to be 29 degrees. So that's going to be over here. So the temperature will get closer and closer to 29 degrees, but it'll never actually get there. So our equation now becomes A times B to the x power plus 29. So the asymptote goes right here at the end, plus 29. Now, we happen to know when time equals 0, so when x is time, and that equals 0, the temperature is 49 degrees. So we put that into our equation. We make time, or temperature 49, A times B to the 0 plus 29. And we get, when we do that, because B to the 0 is going to be 1, so this is going to be 1, going to be A plus 29 equals 49. So I subtract 29 on both sides, and I get A must equal 49 minus 29 is going to be 20. So now we know our equation is something like this. T equals 20 times B to the x plus 29. So step 1, figure out the asymptote. Step 2, put in 0 for the time and figure out A. So A turns out to be 20. Step 3, put in the other data point you have for time. So in this case, we're going to put x, or the t, equal to 0.5. We're going to solve this equation for B. So now I'm put in here when x is 0.5, the temperature is 43 degrees. Put the 43 in there, 20 times B to the 0.5 power plus 29 equals 43. So now I get an equation like this. What I do next is I subtract 29 on both sides. So I get 43 minus 29. And I get 14 equals 20 times B to the 1/2 power equals 14. Now I divide both sides by 20, and I get B to the 1/2 power equals 14 divided by 20 is 0.7. And now, this is a little tricky how to solve that. And, we should talk about this. This is something you know. I want to get it B to the first power. So it's B to the 1/2, and I want to make it B to the first. I'm going to raise it to a power. What power do I have to raise it to make 1/2 into 1? Because a power to a power is multiplied, I have to multiply by 2. So 0.5 times 2 would be 1. If I square this side of the equation, I have to square this side. So B is going to be 0.7 squared. So that is going to be 0.49. So B is going to be 0.49. So my equation now becomes T equals 20 times 0.49 raised to the x power plus 29. So that's the equation of exponential cooling. So that's Newton's law of cooling. Cooling occurs exponentially, going down. And when the base here is less than 1, it will decrease. Now I still need to know the time of death. So to find that, I put 98.6 into the time. Because when he died, his body temperature was 98.6 degrees. And I work backwards and figure out what the time was. So 20 times 0.49 to the x power plus 29 equals 98.6. Solve this. I subtract 29 on both sides. So 98.6 minus 29 is 69.6 equals 20 times 0.49 to the x power. I divide both sides by 20. So I get 0.49 to the x power is divided by 20, 3.48. And now I have a base and the exponent by itself. This is the base, this is the exponent, so they're all by themselves over here. So now what I do is I take the log of both sides and I bring that exponent down. So ln of 3.48, you could use log if you like. I'm going to use ln, 1.247 equals x times ln of 0.49. So now to get x by itself, I just divide both sides by ln of 0.49. And this is going to be times that since death, so divide by ln of 0.49, I get negative 1.75 hours. Remember, time is measured in hours in this case. So negative 1.75 hours, so 1 3/4 hours since time equals 0. And time equals 0 was at 4:42. So 4 o'clock in the morning and 42 minutes. So that would be 4:42 is going to equal 4.6, 4.7 hours, right? Every 6 minutes is 1/10 of an hour. So 42 divided by 6 is 7. So this is 0.7 hours. 4:42 is 4.7 hours. So I subtract 1.75 from that, minus 1.75. I get 5.25, so that's 5 1/4. I don't know how I did that. Oh, I remember, that's a negative. Yeah, my mistake. So I take the 4.7 minus 1.75, and I get 2.95. So 2 hours and 95%. Well, what's 95%? Well, I'm going to take let me get rid of, I just want to find the 0.95 of 60. So 95 times 60 is 57 minutes. So this is 2 hours and 57 minutes, or 2:57 a.m. was the time of death, 2:57 a.m. All right, so here's the equation for cooling. Temperature equals A times B to the x power plus K. And we figured out those three numbers. So you got to figure out what this number is, what's the asymptote, and what's the base. So 3 numbers to figure out there. And then once you get those 3 numbers, you can work backwards and figure out the time it's been since the body was at 98.6 degrees. That was 1 hour and 75 minutes prior to when we found it, and when time was 0, which would mean it was 2:57 a.m. in the morning. So practice that, and I'll give you some worksheets.